in this assignment, I give you some data and I ask you to perform some analysis, but I leave a lot of information out. And the reason I leave it out is that it's typically information that's obtained from a statistician or a master black belt. And as a black belt, you usually won't need to do this. But I'm going to give you a peek under the hood. In case you do have to do it by yourself, you'll see that it's not all that challenging. And also, you'll be able to see what the master black belt or statistician's doing if you have access to that kind of an expert. So typically in a pilot study, in our example, it's a pilot study of an order fulfillment process, you look at a small number of observations and you focus on the individual steps, and then you put the steps together in a computer simulation to see just exactly how the process performed. So for this pilot study, we obtained 50 observations. We ran 50 orders through our new process, and we timed the receive, enter, pick, stage, package, and ship steps, and then we added them up to get the total time it took to process that order through the process. And these data are recorded by computers, so you have a lot of decimal places and so on. And what we want to do now is we want to determine the estimated capability of this process over a large number of orders. So what we want to do to perform that analysis is a simulation, and we're going to simulate 1,000 orders, and we're going to simulate them based on this data. So what we need to do for these data to create a simulation, not we being the black belt, but the master black belt or statistician, is they will need to look at the data and determine what the distribution is that fits it, and then they'll use the information for that distribution to they'll enter that into the simulation, and then Minitab will generate 1,000 simulated values for each process step based on that distribution. So here's how they do it. You go to the Stat menu in Minitab, you go down to the Quality Tools choice, and then down to the Individual Distribution Identification. Now note that our data go from column 1 to column 7, so C7 is the last column. And I make a note of that because when we get to the simulation point, we're going to insert the simulated data starting in column C8. So you click on the individual distribution, and let's not start with enter, let's start with the receive step. Our subgroup size is 1, so there's one order processed at a time. And we'll tell Minitab to use all the distributions and transformations, and then we click OK. Now Minitab does a lot of things under the hood, and we're going to double click in the session window on the distribution identification for the receive process step. And what we're interested in is looking at the goodness of fit tests, and they have a whole list of distributions that Minitab evaluated. Now the ones that say transformation, we're not interested in those. So there are two of those, Box-Cox transformation and Johnson transformation. The reason being they would like to work with our actual data values if we can without performing a transformation on them. Look at the p-values for the ones that are not transformations, and what we're after is the biggest p-value. So in this case, you have for the normal distribution, it's a very small p-value, so that's not a very good fit. For the Box-Cox, it's 0.85, but we don't want a transformation, and the best p-value turns out to be for the log normal. And the log normal p-value is 0.85. That's our best p-value that's a non-transformation. So that's going to be the distribution we want to use. If you look down here at the estimates for distribution parameters, and the letters ML stand for maximum likelihood, you find the log normal row, and you'll see that the location parameter is minus 1.79811, the shape parameter is blank, the scale parameter is 0.75577, and the threshold parameter is blank. So we need to keep these two values in mind. We're then going to go to Minitab, to the Calc window, and then we're going to the random data choice, And we're going to find, excuse me, we're going to find the log normal distribution. Click it. We want to store 1,000 rows of data in column C8. And I've already entered the location parameter from Minitab's table and the scale parameter. The threshold parameter is 0. Minitab had a blank there. And that's, you don't need to know what these are, but basically they are parameters of that particular distribution. Click the OK button, and now if we go look at the worksheet again, you'll see that column C8 has some data in it, and we know that that data is from the receive simulation. So now we have 1,000 simulated receive values, and they're based on the distribution of the 50 that we saw. So we'll just continue that process for the other variables. So in column C9, we'll have the enter simulated values, the pick simulated values in C10, stage in C11, package in C12, and all the way across. So we're going to base these on simulated observations and values. And we just go through the same process. So for enter, I'll do one more for you. Go to stat, quality tools, individual distribution, replace the receive column with the, whoops, wrong column. Click too fast. The enter, again, use all the distributions. Let Minitab crank out this data. Double click on that item in the session window. Pick the highest non-transformation C value. In this case, it's exponential. Make a note of the exponential parameter. In this case, it's 23815. Then go to the data, or the calc window, I'm sorry, random, exponential. Want 1,000 values that are going to go, since we've put the names in, we know that the inner simulation value is going in there. We got to get rid of the C9. We know the parameter is 0.23815. I entered this earlier. And you click OK. Back to the workbook. You now have 1,000 simulations of the enter order process. And you'll do the same all the way across. And then calculate the total in column 14. And that's going to give you the data you can use to determine the process capability, to perform process capability analysis on your new process.